welcome to the deep dive. Today we're plunging into something that honestly sounds straight out of science fiction, but is actually becoming very real. Virtual quantic blueprints, or VQBs.
That's right.
Imagine if you could design quantum hardware, not just physically, but as a kind of dynamic digital blueprint. You could craft whole programmable realities.
Exactly.
So that's our mission today. Explore how VQBs are really redefining quantum computing. Right? From, how a qubit even exists all the way to generating quantum software.
Yeah.
It's a shortcut, really, to getting up to speed on the fabric of future computation.
Yeah.
And I promise it gets really interesting.
Indeed. And we're looking at how these VQBs are sort of moving beyond the, let's say, the immediate limits of current physical quantum hardware. You know, what people call the NASQ era, noisy intermediate scale quantum.
Quantum noisy ones, hard to work with.
Exactly. So VQBs take more of a simulation-first approach. But, and this is key, it's not just about making better simulators for the machines we already have. It's about creating these virtual quantum processors that act as essential infrastructure, defining new, digital ontologies. Computation isn't just a tool anymore. It's like an act of creation itself.
An act of creation. Wow.
And we'll see how this really shifts how we think about and build and, evolve quantum programs.
Okay. Let's unpack that. Virtual quantic blueprints.
Yeah.
Because for a lot of us, quantum computers are still these, mysterious boxes in labs somewhere.
Sure.
But you're saying VQBs let us work with quantum systems in a totally new way, abstracting away some of those really difficult physical problems. How do they actually work?
Well, at its heart, a VQB is a digital representation, a virtual counterpart, if you like, of the quantum hardware.
Digital twin, sort of.
Yeah, you could think of it as a virtual quantum machine, a QVM. And we're already seeing this in action. There are systems like HyperQ, for instance. They use QVMs to tackle real problems in cloud quantum computing, things like resource usage, latency.
Right, practical stuff.
Exactly. HyperQ lets you run multiple QVMs at the same time on just one physical quantum computer. It multiplexes them in time and space. And it works fine with existing programs.
Okay, that's clever.
And then you've got, Google's Quantum Virtual Machine. It gives you a virtual processor that mimics their actual hardware really closely. It even includes noise simulation.
Ah, so you can test how noise affects things.
Precisely. Helps developers prepare for the real world. And Microsoft, they have a Qubit virtualization system too, focused specifically on cutting down noise, helping create more reliable logical qubits from physical ones.
So it's all about using abstraction, this virtual layer, to make quantum computing more practical.
That's the core idea, making it accessible. You don't need to understand, semiconductor physics to use your laptop, right?
Right. Definitely not. It sounds like a really critical step. So now we have this virtual blueprint idea. Let's get into the building blocks. In this VQB world, what does a qubit actually look like? And what about its states? Is it still the 0 and 1 say we usually hear about?
Oh, absolutely. We're still dealing with quantum mechanics basics. Superposition, entanglement, states defined in Hilbert space. That doesn't change. But within the VQB framework, qubits can be, designed, or at least conceptually reimagined in some pretty interesting ways.
Design? How so?
Well, there's this one, admittedly quite abstract research framework, the AI 2-through-1 blueprint. There, they encode qubits as these cubic letter glyphs.
Cubic letter glyphs?
Yeah, sounds weird, I know. But they're embedded with topological metadata. The idea is they're not just zeros and ones in superposition. They're treated as units that could carry, semantic meaning.
Wow, okay. Units of meaning.
And what's really important practically is that a single virtual qubit, or logical qubit, can actually represent a whole pool of physical qubits working together.
For error correction.
Exactly. Pooling them lets you achieve much lower logical error rates. We see this being really effective in, say, trapped ion quantum computers. There's research showing that using 2 virtual qubits per ion in a barium-137 ion chain can simplify the circuits needed for error correction codes.
Makes sense. Fewer errors, fewer gates needed, maybe.
Precisely. It can reduce the number of native gates you need to run, which is a big win.
Okay, that cubic letter glyph idea is still bouncing around my head, but I see the practical side with the virtual qubits improving error rates. So how are these virtual qubits, you call them qubits sometimes?
Yeah, some frameworks use that term.
How are they arranged? How are they connected in this digital blueprint? What's their topology?
Topology. That's absolutely crucial. It defines how the qubits can interact, how entanglement can spread.
Why, there talks to whom?
Exactly. So a VQB defines its qubits and its quantum gates within a specific hardware-aware topology. It usually mirrors the physical layout of the actual quantum chip. There was a paper at Usenix, for example, showing coupling maps for real machines, IBM's I-shape, Rigetti's octagon layout.
Okay.
The VQB mirrors that structure, so the virtual layer knows which qubits can physically interact easily. This mapping is key for running simulations accurately and executing programs efficiently.
So the virtual respects the physical constraints.
It has to, for realism and performance. There's even research into topology-driven quantum architecture search. It tries to optimize quantum circuits by separating the search for the best topology from the search for the best gate types. Shows how fundamental that structure is.
Right, makes sense. You can't just connect everything to everything else arbitrarily.
Right.
Okay, so we have these virtual qubits, maybe even these glyph things, arranged in specific ways. How do we actually make them do stuff? What are the operations?
Right, the action. That comes down to quantum gates. They're the quantum version of classical logic gates like AND or NOT.
Hadamard, CNOT, those guys.
Yep, the usual suspects. Hadamard for superposition, CNOT for entanglement, poly-X for bit flicks. They control the probabilities, change the qubit states. And multi-qubit gates are especially vital, obviously, because that's how qubits interact and get entangled.
And this works the same way on virtual qubits.
Essentially, yes. But what's quite powerful is, going back to trapped ions for a moment, native intra-ion gates acting within a single ion holding multiple virtual qubits, can themselves be multi-qubit gates. They can create entanglement within that ion without needing to rely on the vibrational modes of the whole ion chain.
And those vibrational modes can be noisy, right?
Very noisy, often a major source of errors in that hardware type. So doing things locally, virtually within an ion can be much cleaner.
Okay, that's a neat advantage.
Yeah.
Now, you also mentioned stage-based manipulations. It's not just throwing gates at qubits randomly, I guess.
No, definitely not. There's a structure to it. The process within a VQB often follows pretty distinct stages.
Walk us through them.
Sure. First up is initialization. You set the starting state of your qubits. Often involves creating specific entangled states right at the beginning, like a GHZ state if you need maximal entanglement across several qubits.
Okay, set the stage.
Exactly. Then comes applying quantum gates. This is the core computation part, manipulating superposition, phase, entanglement, running your algorithm, basically.
The actual calculation.
Right. Then, crucially, measurement. This is where you collapse the quantum states down to classical bit zeros and ones. You get your answer out.
The moment of truth.
Yes, but it's also where things can get tricky. Some conceptual models talk about semantic collapse here. Potential distortion or loss of the intended meaning if you're not careful, especially in those more symbolic systems.
Semantic collapse.
Yeah.
Sounds ominous, like losing information in the translation back to classical.
Kind of, yeah, or maybe getting a result that's subtly skewed from the quantum state you thought you were measuring. And finally, there are advanced operations. This stage includes really vital, often complex processes like quantum error correction running underneath, or maybe running a quantum Fourier transform, which is a whole algorithm itself.
Okay, so initialization, gates, measurement, then maybe some advanced stuff like error correction running throughout or at the end.
That's the general flow, yeah.
So back to that semantic collapse idea. How do we make sure everything stays consistent? How do we maintain the integrity of the calculation, especially with noise always trying to mess things up?
Right. Quality control is paramount. Some of those more advanced, maybe theoretical frameworks propose specific modules for this, like something called rectification AI. The idea is it performs semantic Bayrou. Think of it as a kind of conceptual debugging or clarification process to actively prevent distortion during measurement or other manipulations, trying to ensure metaphysical symbolic consistency.
Metaphysical symbolic consistency. Okay, that's deep.
It is. But on the more concrete, hardware-focused side, the field of quantum error correction, QEC, is making huge strides. It's becoming much more practical. We're seeing advanced codes like surface codes being implemented. Real-time checks using stabilizer measurements are becoming more standard.
So active protection against noise.
Exactly. And virtual qubits, as we discussed, play a role here too. By encoding logical information across multiple physical qubits, they naturally lead to lower error rates for these QEC codes, like the basic bit flip code. It makes the whole system more robust.
Okay, so multiple layers of defense against errors and maybe even this semantic collapse, which brings us back to something really fascinating you mentioned earlier, this symbolic layer, the cubic letter glyphs. How does that abstract symbolic language actually connect with the quantum states and gates?
Yeah, this is where it gets pretty mind-bending conceptually. The idea involves something like a qubit symbol designer. It's
Yeah.
about trying to imbue the quantum bits, the qubits, with meaning that goes beyond just their state vector in Hilbert space, giving them semantic or symbolic weight. So frameworks like that AI-231 alphabetic core I mentioned, they use symbolic systems drawing inspiration from, say, Hebrew letters, combined with concepts from crystallography like space groups and other philosophical points they call unity points. It's a very different way of thinking about programming. The goal is to define computational ontologies. You're not just writing code, you're sort of building structures of reality or knowledge within the computation.
Building reality structures.
Wow. Yeah. It aims for a philosophical time logic crystallized into computation, treating things we think of as abstract time, narrative, even entropy, as if are alive, programmable substances.
Programmable time. Programmable narrative.
That's the vision. Imagine a system where you could literally, visually, drag and drop symbolic qubits into entangled lattices, and you'd get real-time feedback on the resulting quantum states, maybe even see a topological map of how they're interacting symbolically. It's highly conceptual, but points towards a radically different programming paradigm.
That is a profound shift. Not just coding instructions, but defining meaning, defining relationships, almost defining a mini reality with symbols.
Right.
So how does that incredibly abstract layer then get turned into something practical? How does it become actual quantum software that could run on Qiskit or Cirq or a real machine?
Well, the VQB itself acts as the crucial bridge. It's the translator. It takes these complex symbolic configurations, these high-level conceptual designs, and translates them into concrete quantum circuits and instructions, mapping them onto standard platforms like QASM or libraries like Qiskit, Cirq.
So the VQB handles the messy details of turning symbols into gates.
Exactly. The goal is always to generate optimized quantum software that runs efficiently. And that involves a whole suite of techniques, both at the VQB level and in the compilers. Things like data compression, reducing the memory needed, using maybe lossless or even carefully controlled lossy compression.
Yeah.
Optimizing data formats, maybe using 32-bit floats instead of 64-bit where possible. Breaking large circuits into smaller pieces, or fusing sequences of simple gates into one more complex, efficient gate.
Standard compilation tricks, adapted for quantum.
Pretty much. And lots of parallelization using multi-core CPUs, GPUs, FPGAs even, to speed up the simulations or control the hardware. You absolutely need fast, accurate simulation tools to develop and test all this, especially because real quantum hardware is still scarce and expensive.
Makes sense. You need to test it somewhere.
And interestingly, the field is borrowing heavily from machine learning hardware accelerators. Why? Because many core operations, like big matrix multiplications, are critical in both fields. So advances there help quantum simulation too.
Fascinating synergy. Okay, what an incredible journey we've taken here. We started with virtual quantic blueprints as this simulation-first way to tackle quantum computing, getting past some of the current hardware headaches.
Right, moving beyond NISQ limitations through abstraction.
We saw qubits get reimagined as potentially meaningful cubic letter glyphs, embedded with topology, how operations are staged carefully, initialization, gates, measurement.
And those advanced operations, including error correction.
Right, and error correction becoming more sophisticated, maybe even with concepts like rectification AI, aiming for that semantic integrity.
Yeah, that metaphysical symbolic consistency. And the real paradigm shift, I think, is that symbolic manipulation layer. Frameworks like AI-231 trying to turn computation into defining reality, using philosophical logic, symbolic languages.
Which the VQB then translates into practical code for Qiskit or other platforms.
Exactly. It shifts the focus from just processing data to actively constructing these programmable realities.
It really does sound like the programmer becomes a kind of demiurge, a creator of worlds within these virtual quantum spaces.
That's a powerful idea.
So as we wrap up, here's something to think about, something for you listening to ponder. If we really can start programming abstract concepts like time, like narrative, using these symbolic quantum blueprints, what genuinely new forms of intelligence, maybe even new forms of existence, could emerge from that? And maybe more importantly, what responsibilities do we have when we start designing these entirely new digital ontologies? That's definitely something to mull over long after this deep dive is finished.